So, what is the true shape of our universe? It's one of those huge fundamental questions, right? And it turns out cosmologists are kind of like cosmic detectives, hunting for clues in the oldest light there is to try and solve it.
And when we say shape, oh man, the possibilities get weird, and they get weird fast. We're not just asking if it's some kind of big sphere. The whole debate really boils down to this simple but kind of wild idea. Are we living on an endless flat sheet of paper that just goes on forever? Or is it something way stranger, like a giant cosmic donut?
Okay, so to even begin to answer that, we have to get one thing straight. There's this super important distinction we need to make, and it's really the central clue in this whole mystery. We're talking about the difference between the universe's curvature and its shape, or, its topology. They might sound like the same thing, but they describe two totally different properties of space.
All right, check this out. On one side, you've got geometry. Think of it as the local texture of space. At any single point, is it bent like a ball or is it flat like a table? And that's all decided by the stuff inside the universe, all the matter and energy. But then on the other side, you have topology. And that's the big picture, how everything is stitched together globally. And here's the kicker, the really important part. Einstein's theories, they tell us a ton about geometry, but they have basically nothing to say about topology. So a flat universe could be infinite, or it could be finite and loop back on itself. We just don't know from that alone.
So let's follow that first lead, right? Let's talk geometry, because this is something we actually can measure. All we have to do is add up everything in the entire cosmos. Easy. So let's see what the evidence says about that local curvature. Okay, so the key idea here is this thing called critical density. The best way to think about it is like a cosmic balancing point. Imagine a scale. If you pile on too much stuff, more than this critical value, gravity wins and the whole universe curves in on itself like a ball. If there's not enough stuff, it expands forever and curves outwards like a saddle. But if you get it just right, if the density is exactly at that critical value, boom, it's perfectly geometrically flat. So, astronomers went out and did the cosmic accounting. They added up all the normal matter, stars and planets and us. They added in all that mysterious dark matter, and then they added in the even more mysterious dark energy. And what they found is just incredible. The total amount of stuff is astonishingly close to that critical density. This number we call omega, it's basically 1, like dead on. And an omega of 1 points to one single, overwhelming conclusion for the universe's geometry. It's flat. It's not spherical, where parallel lines would eventually cross, and it's not hyperbolic, where they'd fly apart forever. Nope. It means that, on a cosmic scale, the universe follows the same basic rules of geometry you learned in high school. Parallel lines stay parallel. Pretty neat, huh?
So, case closed, right? Flat geometry means infinite sheet of cosmic paper. Done. Well, not so fast, because this is where our little detective story takes a really mind-bending plot twist. See, flat doesn't automatically mean infinite.
All right, so let's recap. Our best evidence is screaming at us. On a local level, space is flat.
And, the easy, simple assumption is that this flat space just keeps going forever, an infinite grid in every direction. But what if that's wrong? What if the simplest answer isn't the right one? What if you can have a universe that's perfectly flat, but is also finite and loops back on itself? I'll say hello to the 3 torus. This is probably the most famous example of exactly that, a universe that's flat, but also finite. Yeah, we call it a cosmic donut, but a better way to think about it is like an old-school 3-dimensional video game. Locally, every part of it is flat, but globally, the whole thing is connected in a really, really weird way.
So how would that even work? Okay, imagine you're inside a giant cosmic cube. You hop in your spaceship and fly straight towards the top wall. But instead of crashing, you just reappear, coming up from the bottom floor. It's like Pac-Man. The same thing happens if you go left, you come out on the right, go forward, you pop out from the back. The result? Looking out into space would be like being in a crazy cosmic hall of mirrors. You'd see endless copies of our own galaxy over and over. And yeah, in theory, if you had a telescope powerful enough, you could literally see the back of your own head just by looking far enough in one direction.
Now, I know this sounds completely like science fiction, but here's the cool part. It's actually a testable idea, and astronomers are, right now, actively hunting for the evidence of this Hall of Mirrors effect, and they're doing it by looking at the oldest light in the entire universe.
And our star witness in this case? It's the cosmic microwave background, the CMB. This is literally the afterglow of the Big Bang. It's the super faint light that fills the whole sky, and it's basically a baby picture of the universe. It comes from this imaginary sphere all around us called the surface of last scattering, which is just a fancy way of saying it's the absolute farthest back in time we can possibly look. Okay, so here's the key bit of logic. Follow me on this. If the real universe, the donut, is smaller than the bubble of space we can see, then that bubble has to overlap with itself. Think about it. Light from one single spot in the early universe could travel all the way around the loop and hit us from two totally different directions. And that overlap, it would leave a very specific, undeniable fingerprint all over our map of the CMB. And that fingerprint is what scientists are looking for. They call it the circles in the sky method. These overlaps would show up on our CMB map as pairs of matched circles. And I mean perfectly matched. The pattern of hot and cold spots inside one circle would be an exact mirror of its partner circle somewhere else in the sky. If we found just one of these pairs, that would it, the smoking gun, conclusive proof that our universe is a finite looping cosmos.
So, have they found them? Did our cosmic detectives find the circles and crack the case? Well, this is where the plot thickens, and the mystery gets even deeper. After all these years of searching, and I mean painstakingly combing through these incredible high-res maps from satellites like WUPMAP and Planck, the result is, well, it's nothing. Zilch. Not a single definitive, statistically significant pair of matched circles has ever been found. But wait, finding nothing is actually a really powerful clue in itself. It doesn't completely rule out the donut idea, but it does tell us how small it can't be. What the data says is, if the universe is a repeating loop, then that loop has to be at least 27.9 gigaparsecs wide. And just to put that in perspective, a gigaparsec is over 3 billion light years. So we're talking about a ridiculously huge minimum size. Okay, now get ready for this. Let's compare that minimum size to the size of the entire universe that we can actually see, our observable universe. The diameter of what we can see is about 28.3 gigaparsecs. Do you see how crazy close those two numbers are?
The implication here is just stunning. It means the smallest the real universe could possibly be is almost the exact same size as the universe we can see. So if we are living in a cosmic hall of mirrors, the room is so huge that our entire view fits just inside one of the tiles. The reflections, those fingerprints we're looking for, would be just outside our line of sight, just beyond our cosmic horizon. It means the universe could totally still be a donut, just one so big we can't see the hole yet.
And yeah, this cosmic case file is far from closed. There are still these weird, lingering tensions in the data. So while the CMB on its own screams flat, some other measurements hint that maybe, just maybe, there's a tiny bit of curvature after all. And what's even more tantalizing are these strange, large-scale patterns in the CMB that the simple infinite universe model has a really hard time explaining, but which some other weird finite shapes, like a Poincare dodecahedral space, which is kind of like a cosmic soccer ball, they actually predict those anomalies. So the mystery is very much alive.
So where does that leave us? Well, it leaves us with one of the most profound questions you can ask. Are we living in a truly endless cosmos that just goes on and on forever? Or are we living inside a finite repeating illusion, a cosmic hall of mirrors so vast that we just can't see the reflections? Yet, the hunt for that answer is one of the most exciting things happening in science today.